and share the screen. Okay. Okay. All right. Good morning, everyone. I hope you can see the screen and also hear me. So today we will continue with our review, and I think today may be the last class of reviewing probability. So conditional probability mass function. So we will look at it first and then go to conditional expectation. So let xy be a two-dimensional discrete random variable. And let us say little f denote its probability mass function. Let f sub x and f sub y denote the marginal probability mass functions. So the conditional probability mass function of x given y, capital Y equal to little y, that is basically probability x equal to little x given probability y, given probability y equal to y. So that is defined by, kind of formal fashion. It is the joint density, that is the joint probability mass function fxy at this x and this y, divided by the yth marginal, the marginal fy at y, provided the denominator is positive. And it is given to be 0 otherwise. So that is the definition. So whenever the denominator, that is, this is strictly positive, you can note that it is same thing as what we have seen earlier as conditional probability of events. So note it down if you want to.
Sir, I think someone's mic is on, a sound is coming.
So this appeal is to everyone. Whoever's mic is on inadvertently, please kindly switch it off so that it doesn't disturb others. Thank you very much. Okay. Now, in a similar fashion, conditional probability mass function of y given x equal to little x can also be defined. Fine. Now note that suppose you want to find, say, let us say for a nice subset A in the real line, like an interval and things like that. If you want probability x takes value in this set A given y equal to little y. So what you will do is you will sort of add up all the conditional probabilities as x varies over the points of A, and that precisely this. Each of this item is basically probability capital X equal to little x given y equal to little y. So you are adding over those x's which are coming from A, and it is this. Again, it is something which you already know. And this basically is kind of either you can derive it directly, or it is the underlying idea is this exercise. Suppose f sub y at little y is strictly positive. Then you consider this thing as a function of x alone, keeping y as a parameter. Y is fixed. Then x going to little f at x given y equal to little y is a one-dimensional probability mass function. Sorry, note it down if you want.
So basically, in some sense, we can say that fxy is a two-dimensional probability mass function.
Pardon?
Fxy is a two-dimensional probability mass function because
that original fxy, it is given to be a two-dimensional probability.
okay.
Yeah. I mean, for these things, you need this little f a priori. You should know it. Okay. Without knowing the conditional probability, the probability mass function, in general, you will not be able to find the marginals. Of course, in some problems from the data given, you may be able to have an idea of the left side here, the conditional probability mass function, and so on. But sort of in a logical way of doing things, you should know the joint probability mass function to get hold of, and also the marginals, and to get hold of the conditional probability mass function. Yeah. So we will look at example, Bernoulli trials, again revisited. Notations as in Markov chains 2, this means that whatever I did that till yesterday after the Markov chains 1 will be uploaded. It is just that some typos I found that have to be rectified. I will do it today itself. And let T sub R be the number of trials until the Rth success. We are going to take R equal to 1 and 2. So T2, see, T2 is the number of trials until the second success, which means the first success must have already occurred. So it is clear that 1 less than or equal to T sub 1, strictly less than T sub 2.
Sir, have you uploaded the PDF Markov chains too?
Not yet. That's why I said it needs some typos have to be corrected. I will do it. I said no.
Okay.
So now, suppose you know that T sub 1 is equal to 10. From that, you already have the information. T sub 2 has to be at least 11. So some information about T2 is known once you know T1, and vice versa. If you know that T2 is 100, T1 can only be up to 99. Consequently, T1 and T2 are not independent. So we will first find the joint probability mass function of T1 and T2, and then the conditional probability mass function of T1 given T2 equal to n. Okay, please note it down if you want. Okay. Now, from our earlier discussion, recall that W1 is same thing as T1, and T2 is precisely W1 plus W2. Also, from our earlier discussions, we know that W1 minus 1 and W2 minus 1 are independent discrete random variables. Each have a geometric distribution with parameter P. Okay, now let N1 and N2 be integers greater than or equal to 1, and also N1 is strictly less than N2. So because what we have here, T2 is expressed in terms of W1, W2, etc. The event T1 equal to N sub 1 and T2 equal to N sub 2 is same thing as W1 minus 1, that is a number of failures before the first success, is N sub 1 minus 1, and W2 minus 1, that is the number of failures after the first success and before the second success. That is N2 minus N1 minus 1. You can easily see this. So this event is precisely equal to this event. So this event now we have expressed as the intersection of two events which are basically independent, because these random variables are independent. So therefore probability T1 equal to N1 and T2 equal to N2 is same thing as probability W1 minus 1 equal to N1 minus 1 and W2 minus 1 equal to N2 minus N1 minus 1. So since, and this probability is probability of W1 equal to N1 minus 1 multiplied with probability W2 equal to N2 minus N1 minus 1. Since these things have geometric distributions, you know the exact expression, and plugging those things, you finally find that probability T1 equal to N sub 1 and T2 equal to N sub 2 is P squared multiplied with 1 minus P whole to the power, that to the power N sub 2 minus 2. These are all just simple steps. So now we have to write down the joint probability mass function. Note that we have observed this only for N1 and N2 integers which are here. To know the joint, the probability mass function, you should be able to specify everywhere. So we have this. So hence the joint probability mass function of T1 comma T2 is given by probability T1 equal to N1, T2 equal to N2 is P squared times 1 minus P to the power N2 minus 2 if 1 less than or equal to N1 less than or equal to N2. Note that in this expression, the dependence on N1 comes from here. So it is not that this joint probability is depending only on N2. It is also depends on N1. Over which region? And it is 0 otherwise. In your earlier course also, you would have seen such examples where the random variable T1, T2 takes value not in a rectangular kind of region, but it could be triangular kind of region. So observe that if T2 equal to N, then T1 can take only the values 1, 2, up to N minus 1. So that now, and the T2 has to be at least 2. So let this N be greater than or equal to 2. That be fixed. Then by our discussions of the previous few classes, we have probability T1 equal to K given T2 equal to N is by definition probability T1 equal to K and T2 equal to N divided by probability T2 equal to N. So this expression, the numerator we have from the previous page, and the denominator you can look up our notes or your slides or whatever notes you have taken during the class hours. Then you will find that this is precisely 1 divided by N minus 1 for K running from 1 up to N minus 1. It is again fairly intuitive in the sense that if you know that T2 has occurred at the 10th step, then once T1 occurs, the conditions of the experiment remains the same and so on. So therefore, the obvious guess would be the first success would have happened at any of the previous points in an equally probable fashion. So thus, if we know that the second success has occurred at the nth step, the conditional probability of first success having occurred any of the preceding n-1 steps is 1 over n-1. So in a similar fashion, you can find conditional probability mass function of T2 given T1 equal to K, where for any K greater than or equal to T2 has to be bigger than T1. So if K is equal to 1, T2 can take value from 2 onwards. Note it down if you want to. Okay, note it down. Right. Conditional expectation. Conditional expectation is basically taking expectation with respect to that conditional probability.
Sir,
Yes?
can you show the previous link just
Yeah,
one?
sure.
Thank you, sir.
Okay. So conditional expectation is basically taking expectation with respect to that conditional probability function. So with the notation above, as before, conditional expectation of capital X given y equal to little y. So that is defined by conditional expectation X given capital Y equal to little y, that is summation over X times F, little f X given Y equal to little y. So this f X given Y equal to little y we have seen earlier. So this provided this sum converges. So this is what I was alluding to earlier. Conditional expectation is expectation with respect to the conditional probability mass function of this thing. So if the marginal probability mass function at little y is strictly positive, then this you can also write, since this can be written xy probably phi of xy divided by this, you can observe this. Note it down if you want. So this particular definition or this equation, we are referring it by dagger, this symbol, because we will recall it, or rather we have to refer to it later. So I'll go over to next slide. Now suppose the expectation of the random variable X exists. Okay. Then note that if you see this, if you take this quantity and multiply that with, see, this is the probability that y takes the value little y, that is f sub y, y. If you, for each y, if you take this product and then sum over y, sum over y meaning all those y's for which this is strictly positive. Because for this thing which is 0, this is not going to have any contribution from that. And therefore, by what we have written down here, we can write it this way. But this cancels with this. So what you have is, the net expression is summation over x, summation over y, x times fxy. For all xy for which fxy is positive. And which precisely is expectation x we have seen in the last class. The expectation of x you are representing in terms of the two-dimensional probability mass function. Note it down if you want. Yeah. What I would suggest is, when we go to the next slide, we will be making use of this one, which I have denoted by dagger, and the other one double dagger. So if you are not taking down notes, please, if you have a piece of paper, please note it down for your convenience. And similarly, note this also, along with the thing that this happens if expectation x exists. So if x exists, then we have this quantity is equal to expectation x, the left side and right side. That is our double dagger. Okay, I shall go to the next slide. Okay, now we begin with an observation. From that single dagger, note that this conditional expectation of x given y equal to little y is a function of y. Function of little y. Denote this function of little y by psi. That is, psi at y is expectation x given y equal to little y, or y in R. So this psi is a function from the real line to the real line. Now observe that our random variable y is a function from the basic probability space to the real line, and this psi is a function from real line to real line. So one can consider the composition, psi composition, capital Y. So that composition we denote by psi y is a function from omega to R. So since it is a function from omega, this at a little omega we should specify. So psi y at a little omega is expectation of x given y equal to little y if y omega is equal to y. By this recipe, we have got a new real valued discrete random variable. Is the sort of the intuitive idea clear? In other words, the conditional expectation, now we want to view it as a random variable. This idea is useful when we have a look at martingales later in the course, towards the end perhaps. So this is one thing which you might not have seen in your earlier courses. And this particular thing I have sort of followed Carlin and Taylor in the first chapter of Carlin and Taylor. It may be given in other chapters also, other books also. Carlin and Taylor, first course in stochastic process. But generally, I will not be following Carlin and Taylor. I have several books like this thing, but mostly it will be that once the Markov chains and all, it will be for quite this thing, the Boyle-Porton-Stone stochastic process. I will give that detail later. Okay, please note down if you want. Okay. Now note that that double dagger can be written as expectation of psi y equal to expectation x whenever expectation x exists. And also we will call this random variable as conditional expectation of x given y. Whereas earlier we were talking about conditional expectation y equal to little y. So this conditional expectation random variable, from what we have seen in the previous slide, it is clearly a function of the capital Y. And also this double dagger can be now written as the expectation of the conditional expectation of x given y is expectation of x, provided expectation x exists. This also sort of gives you an idea that when x is a random variable such that it has finite expectation, the conditional expectation x given y can be defined. We are not going into such technicalities. That is, for those things you may need measure theoretic machinery. But the intuitive idea is fairly clear. Please note it down. Okay, so we will sort of, to get this kind of idea somewhat concrete in our mind, we will look at a concrete example. So namely, once again, Bernoulli trials. So we have already shown that if little n is greater than or equal to 2, then the probability, conditional probability mass function of T1 given T2 equal to N is given by probability T1 equal to K given T2 equal to N is 1 over N minus 1 for any K between 1 and N minus 1. So we get the conditional expectation of T1 given T2 equal to N. So that is conditional expectation T1 given T2 equal to N. So this conditional probability mass function is 1 over N, and this varies. In this case, T1 can vary from 1 to N minus 1. It is precisely this sum. So this doesn't depend on K, that comes out of that and so on. What you have other, that sum, if you evaluate, and the whole thing is half of N. So before I go to the next slide, what is now the conditional random conditional expectation random variable conditional expectation T1 given T2? What is that random variable in this context? The answer is staring at you. Anybody? Come on, guess. What is the random variable conditional expectation T1 given T2? I think if I go to the next slide, many of you would regret for not having taken the plunge and taking the guess. Okay, it is just half of T2. See here, this is N, T2 equal to N and N by 2. So it is just that. So the conditional expectation random variable, conditional expectation T1 given T2 is half of T2. So T2 given 10 of T1, it takes any of the 9 values in a uniform fashion, discrete uniform. So the mean of that is going to be some kind of a midpoint of that. That is half. That is average value. And the expectation of T1 is easy to find. So from our spade suit, this guy, we immediately get, it is this. This last equality is the exercise here for you. And note here, this conditional expectation, this is a function of T2. This obviously is a function of T2. Okay. Note it down. Okay. Now we will list certain properties of conditional expectation as a random variable. And most of these are easy to prove, but anyway, we will assume them, assume all these things. And in what is going to follow here, the G will denote a function on the real line such that expectation of mod Gx exists. And similarly, any f which you will find will be a bounded function on real. So the first property is what we have seen earlier. If you assume that expectation of x exists, that is, if x is integrable, rather summable, since it is a discrete random variable, summable. Thank you. I mean, sorry for bringing in suddenly integrable and so on. If expectation exists, mean exists, then this conditional expectation of x given y, that random variable also exists, that is, it is well defined, and it is a function of y. And also, expectation of conditional expectation x given y is precisely expectation x, provided, of course, expectation x exists. Similarly, instead of x, you have a gx. So gx is integrable. So by this, the first property, you know that conditional expectation gx given y exists. And subject that to this property, you get this one. Suppose x and y are independent random variables. Then conditional expectation gx given y. See, since x and y are independent, gx and y are also independent. So any information concerning y will not have any effect on gx. Therefore, conditional expectation of gx given y is precisely expectation of gx. This is the intuitive argument. You can also prove it easily. For example, to start with, the conditional probability mass function x given y equal to little y, that will not have any dependence on y. So that f of small x given y equal to y will be just fx, f sub x at x, the marginal at x. If this guy x happens to be itself a function of y, this guy there, the other extreme, instead of independence, x depends on y. So that, let us say, we denote by f of y. So expectation of f of y equal to y. I mean, sorry, expectation of f of y given y is precisely f of y, this itself. In particular, for example, conditional expectation y given y is y. So here, note that g is a function such that g of x is integrable and f is a bounded function. So conditional expectation gx times fy given y can be proved. It is this fy can be taken out of this thing like a constant, multiplied with conditional expectation gx given y. And also using that Spade suit, that equation here, etc., you can easily see this. Actually, to see this first equation, you first consider conditional expectation gx times fy given y equal to little y. Then the next step, that little y can be plugged in here. So f at little y is a constant, so that comes out of the conditional expectation, that expectation. I mean, to see this, I will add one more line here, or one more property in the notes. I should have done it, but now that I realize it is better to do that, I will do it. If G is non-negative, then conditional expectation of Gx given Y is also going to be non-negative. So it preserves positivity. Let x1 and x2 have finite expectation, then for any constants, real constants a1, a2, sorry, there is an error here. This is not equal to, this should be a plus. Please correct it. Conditional expectation a1, x1 plus a2, x2 given y. This is a plus here, please. I'm sorry for this typo. Is a1 times conditional expectation x1 given y plus a2 times conditional expectation x2 given. So in other words, the conditional expectation operation is linear in the first variable, in the numerator. So please note down these properties. We will have quite a few occasions to see many of these properties when we do martingales. I hope, because many things will depend on traditional topics, depending on time, etc. etc. Okay, I'll go to the next. So an extension, this again we will need when we do martingales. So in other words, in all these things, this y here, this is a real valued random variable. This we may need to substitute with a vector valued random, not the numerator, but the denominator. Yeah. So let f denote the probability mass function of the, let us say, 1 minus m dimensional discrete random variable x, comma, y1, y2, ym. Earlier we just had y, so now we have m dimensional random. Let f sub y denote the probability mass function of the m dimensional random variable y1 to ym. Then the conditional probability mass function of x given y1 equal to little y1, etc., ym equal to little ym is defined by, this is the symbol for that, little f at x given y1 equal to little y1, etc., ym equal to little ym is the joint probability mass function, that is 1 plus m dimensional joint density, joint discrete mass function, f x, comma, y1, y2, ym divided by f sub y, y1, ym, provided the denominator is non-negative. It is 0 otherwise. Oh, this should be a e, otherwise. Yeah, w and e are adjacent keys. Also, similarly, the conditional expectation of x given y1 equal to little y1, etc., ym equal to little ym is given by, as before, the same kind of summation over little x of the conditional probability mass function, provided the sum converges. As in the earlier case, the conditional expectation of x given y1, y2, ym is a random variable and is a function of y1, y2, ym. And this happens. And provided this random variable exists, if expectation of x exists. All these things go through. Yeah. So that is all for today. So if you want to copy or want me to go over to some other slide, previous slide, I can do that.
Can you show the previous slide?
The idea is same as the one dimension, the lower dimensional case. It is just that notationally it is somewhat slightly complicated. That's, I mean, more. I shouldn't say even complicated, more elaborate. It involves more writing. That's it.
Okay, sir.
Okay. So today's material, it's alone, I have called it as Markov chains 3. 2 will soon be put up. 3 also I will try to do it today. And maybe I will, by at least early next week, I will give you the first problem set. So I shall stop sharing. And if in case there are no comments or questions.
Sir, when will you give the first problem set?
Probably early next week.
Early next week. Okay.
Hopefully. Yeah. Okay, I shall end the session.
Thank you, sir.
Take care, and we will see on